This is lecture 11B on sequences, and this is a totally arbitrary lecture. If you're not interested, then you don't have to follow this lecture. But if you have an interest in mathematics in general, you might want to just look at this lecture and pick up some new ideas and some new vocabulary. The main idea I want to introduce is the idea of Cauchy sequences. And this has to do with, just think again about all these, the precise definition of the limit and how we tried to test for limits. Basically, we had to have the limit in mind. We had to have an L and find out if the terms were within L plus or minus epsilon for all n greater than some capital N. In other words, we had to have the limit, we had to have a proposed limit to test if there is a limit. Now, when you think about it, that's sort of, but there's another way to look at it, and this is called the Cauchy criteria for convergence. It does not require that you have a proposed limit. What you do instead is look at the difference between the terms. This isn't necessarily the difference between adjacent terms, it's the difference between all combinations of terms greater than some index, which I'm going to call n. And here's the Cauchy criteria. If for any epsilon greater than 0, there exists some n such that for any two numbers with m, n, or any two terms of the sequence with m and n greater than n, their difference is less than epsilon. So if you start at 10, you would have to look at all the combinations. You'd have to look at 12 minus 11 and 45 minus 11 and 13 minus 22. Okay? You have to look at all of them. Well, you don't have to. You have to have an algebraic way of doing this, of course. But the Cauchy criteria states that if for every epsilon you pick, you can find some number n, right, such that for all terms greater than n, their difference is less than epsilon. If the sequence satisfies this criterion, it's called a Cauchy sequence. Every real Cauchy sequence is convergent. And also, every convergent sequence is also Cauchy. So in this proof, I'll show you that every convergent sequence is Cauchy. So let's let the sequence a to the n be a convergent sequence and converge to some limit L. So the precise definition of convergence states that for any number epsilon, let's call it epsilon over 2 instead of epsilon to make things look nice at the end. So for any epsilon over 2, there exists an n such that a to the n minus n is less than epsilon over 2 for all n greater than this capital N. Now, consider two numbers, n and m, both greater than n. Now, we're going to use a triangle inequality here, but I want to look at the absolute value of n, a to the n minus a to the m. This is our Cauchy criterion right here. All right, and this had better be less than epsilon. Right. Well, a to the n and a to the m, I could write this as a to the n minus L plus L minus a to the m. All right, I'm getting plus and minus L in here, which of course changes nothing. Now, by the triangle inequality, those terms in parentheses, the absolute value of them is less than or equal to the absolute value of each one of the parentheses separately. Right. Now, I know that a to the n minus L is less than epsilon over 2 because I said that the sequence converged to L. Right. Also, m is greater than n as well, so L minus a to the m is less than epsilon over 2. Also, they're less than epsilon. This shows that a to the n minus a to the m in absolute value is less than epsilon. So this convergent sequence satisfies the Cauchy criterion. There's a lot more to say about Cauchy sequences, and if you study mathematical analysis, you will learn much more. But I just want to introduce the idea of a Cauchy sequence with the idea that there is a way to determine convergence without first proposing a limit. The next question I want to answer here briefly is, are limits unique? If I found one, is there not another? Okay, the answer is the limits are unique. So to prove this, I'm going to propose that there are two limits and then show that they're equal. I'll have to use a triangle inequality again. Okay, so let's say that L1 and L2 are both limits of some sequence a to the n. That is, a to the n converges to L1, it also converges to L2. So by the precise definition of convergence, for every epsilon greater than 0, there's a number, and I'm going to call it M1. Instead of that capital N, I'll call it M1 just to give it a name, such that the difference between the sequence and its limit L1 is less than epsilon for all n greater than m1. It's also true that there is some m2 such that an minus that second limit is less than epsilon for all n greater than some m2. All right, those are both precise definitions, precise statements of the convergence of the sequence to some limit L1 and precise convergence of the sequence to the limit L2. Now let's let n, I'm going to color here, n be the minimum of those two numbers, okay, of m1 and m2. I know that for n greater than n, let me look at this. I'm going to take the difference between L1 and L2, and I'll do the same thing I did before, but instead I'm going to remember that other proof. I added plus or minus L. Here I'm going to add plus or minus a to the n. So L1 minus an plus an minus L2. All right, that's fine. Break these up into parentheses. Use the triangle inequality, which shows that the absolute value of L1 minus L2 is less than or equal to L1 minus an plus L2 minus an. They're both less than epsilon. They're both less than epsilon, so the difference between L1 and L2 is less than 2 epsilon. L1 minus L2 is a non-negative number. Epsilon is arbitrary, so the difference is 0. This implies that L1 equals L2. The last thing, let me state that again. If you have a positive number, it's less than any arbitrary epsilon. Right? It's strictly less than any arbitrary epsilon, then that is less than the difference is 0. Because I could always set epsilon to be a smaller and smaller number. Okay? So L1 equals L2. In other words, if you think you have two limits, you really only have one because they're equal.